Welcome again, everybody. This is Enrico Signoretti. I am head of product strategy at OpenIO, and I'm glad to be here with you today to give you an update about our company and the work that we are doing around object storage and data processing. I hope that all of you can already see my screen. Also, please, there is a button in your dashboard where you can raise an hand, so we can make this session interactive. Every time you need to talk, ask a question, just raise an hand, and we will unmute you. And so, let's start the presentation. So all the slides that you will see will be not under NDA or embargoed, but actually some of the features that we are going to discuss could be modified between now and the date of release of the software. So be careful when we go in describing these features in your articles. Before doing something, please ask. That will help to get the best explanation and the best idea on what we are doing. So in this presentation, I will give you a quick company update, and then I will talk about our product, which is SDS, an object storage platform. And after that, we will talk about Grid4Apps, which is our compute framework integrated in SDS, and it's event-driven. So you will, by using this software, you are able to run code directly into SDS driven by events. So about the company, for who doesn't know OpenIO, it's the company started in 2015, so it's a very young startup. Actually, our product is very mature because the development started in 2006 from an idea that the founding team had in the day to solve a problem for a big French customer in here in Europe. And so in 2007 the design started, and the first cluster went in production in 2009. The second cluster in 2014 was 15 petabyte when all the team left and decided to found OpenIO. In the meantime, the software was open source. So this is why OpenIO, this is how OpenIO got his software. Very briefly, the team is quickly growing. We had 7 new hires in this year, but we are also hiring in the US our first salesperson and pre-sales. Also, from the point of view of the business, we just won 3 major multi-petabyte installations in May, and as well as some smaller ones. We are signing agreements all across Europe for partnerships for the selling, and we are also we hope to sign a couple of new partnerships also in the US this month. So if you look at OpenIO from the market perspective, you can see that the market is now focused on 2 different verticals. One is latency focused kind of applications, so databases and all the kind of application that needs a very low latency, consistent latency. In this case, you can find a lot of I/O per second. On the other side, you see capacity focused application. They need a very good price point in terms of price per gigabyte. The data is modified less frequently, Sometimes it's written once and never changed, and usually there is also a difference in the type of architecture. So most of these applications are in the software-based realm, while when you look for latency, because NVMe, because products, but also because the layout of and the architecture of the design of the arrays, most of them are hardware-based. And why object storage? I usually show this slide just to show the difference between the different types of storage. Sometimes we forget that object storage is the only one that is actually internet accessible, because the protocol used for communicating with it, and usually the same information is accessed by millions of devices at the same time. Also, this kind of system are all scale out, and they can really scale up to hundreds of petabytes. So sometimes now you can hear about system reaching the exabyte level. We do two things. Okay, one is object storage. So traditional object storage use cases, email platform. So each single email is an object. It's a perfect object actually, because you have the content of the email, which is the data and all the information that describe the email, including recipient and so on. Oh, I see all the tweets coming. And other use cases for us are media entertainment with large video repositories, for example, private cloud storage, sync and share, for example, is a good use case. Remote storage consolidation with remote gateways consolidating in a central repository, backup and archiving, and big data. This is very classic use cases. At the same time, we are able to serve next generation applications, because we have an integrated data processing engine, and of course this can be the base for industrial Internet of Things and machine learning kind of application, and I will talk a lot about this in the next slide. So we build infrastructure for the data-centric era. What does it mean? Of course, structured data is the first thing, and you know how much data we are saving every day, images, videos, and just think about the size of the video. So we moved very quickly from small videos, now very large videos, and now 360 video is becoming a thing. And at the same time, not only images or pictures, but actually big data application, or even logs. So even a small data center can create a huge amount of log every week. Industrial Internet of Things is another big wave coming. So a lot of companies are looking at a strategy for Internet of Things. So they are redesigning new devices with IP ports, with the Ethernet ports, with the Wi-Fi on top of that. They can collect huge amounts of data, and they can send this data to a central repository for big data analytics or whatever. And of course, machine learning and AI. If you think about the fact that machine learning, most of it is basic on statistical analysis and pattern matching. You can think about how much data you need to make these algorithms effective. And again, after years of talking about cloud, only cloud, we are going, everything is going to the cloud. Actually, a new sort of edge application are coming out, where you see the connected cars or platform, offshore platform in the middle of the ocean. Okay, these guys can't rely on the cloud for their compute tasks and data. Okay, yes, connected cars are connected, but actually you want to process some data locally. You don't want to send a picture you're taking on the street to the cloud, get it processed and get it back, because if you do that, probably you already killed someone on the street. And the same goes for other applications. Okay, so face recognition and next generation application that take advantage of all of this. And they, for example, thinking about an airport, I don't know if you remember Minority Report with Tom Cruise a few years back, and so there was this advertising system that was based on the fact that they were scanning retinas, and they projected specific advertisement for people. Yeah, okay. The same thing is now possible with this modern system that we have in face recognition. So they can face recognition your face, but actually they can recognize also how you are dressed, what you are carrying on. And in function of that, this system can decide to change your route in the airport and to send you to the right shop or in front of the right shop before going to the gate. Of course, if this kind of task is offloaded to the cloud, the time that you take the picture, you send the picture to the cloud, and you get it back, it's not compatible with the timing of you walking through the airport. So maybe you just pass the sign before the results comes in. So let me talk about SDS, our next generation object storage. First of all, we don't describe our platform as a storage system, but as a storage infrastructure, because it's we build this kind of infrastructure that are compatible with S3, Swift, and our APIs, and they can serve multiple workloads at the same time. Okay, this is very common with most of the object storage system indeed, and but the idea is that this kind of infrastructure, contrary to what you usually see in the traditional storage system, it's really multi-tenant, and it's not only that it can serve multiple workloads at the same time, but actually also several users at the same time. Okay, so you can have application users doing the same thing, but also different application with different kind of data in the same system. And one thing that I usually say, just the day I joined OpenIO, I started with this idea that object stores are all identical. Okay, you can expect from them a very long list of features now, but actually they are very, very similar. So all of them can do geo-replication, all of them can do S3 protocol, all of them can do scale out, and so on. So it's not it's no longer the differentiator. Okay, and so are we here to talk about another object store? Actually not. So we are different from other object stores for three reasons. The first one is that yes, we can take commodity hardware and our software to be the hyper scalable storage platform, but we actually can do also compute on top of it. And there are four main technologies that we leverage to do that. The first one is that we don't use a distributed hash table like in the most of our competitors. Okay, we use what we call a system of directories, so that the hash table is distributed in several directories, and the idea is that it's much more flexible to distribute data in these directories, and it's faster. The other thing is that we don't do rebalancing. The idea is that you can add every new resource to the cluster, like adding a disk, adding a node, and it's immediately available without rebalancing. How do we obtain that? Actually, we have a small agent running in all the nodes. This agent collects data from the nodes, including compute, memory capacity, storage capacity, throughput, and so on. It's a formula, so we can implement it depending on the needs of the customer, and we compute a score at the end, a quality score. So each node has a score, and we always select the best node for each single operation. So when you read or when you write, all the operation goes to the nodes that have the best score at that moment. And on top of it, again, we have grid for apps, so we can collect each single event from the cluster and run applications directly from it. So I see that someone has a question. If using direction, doesn't that mean that you have to do equivalent of SGK data corruption? Walk you through. No, actually, we have a mechanism inside the cluster to automatically rebuild the information. So each single component of the tree already has the information to reach the upper level. It's a little bit complicated. I'm not actually technical. I can do a follow-up on this with Chris later, just to explain better how it works. So the other thing about our architecture is the lightweight design. So our system can run in one ARM core and 500 megabytes of RAM. It means that we can run in a very large data center cluster, but also on a $5 computer. This has some advantages. One is that we are able to build this kind of device. So if you look at this, this is what we call a nano node. It's a traditional SATA hard drive, and in front of it you can see a small PCB. It contains RAM and an ARM CPU, 2 Ethernet ports, and some SSD. Okay, this is a complete functioning Linux-based hard drive at the end of the day, and it has a couple of advantages. One is the failure domain is very, very small, so we can pack up to 90 of these disks in a single chassis. But the difference between this and a 90 disk server is that if you fail, if you lose one of these nanodes, one of these server, you just actually use a disk. If you lose a 90 disk server, the failure domain is pretty huge. This is an information that I'm giving you just to let you know that in the very near future, an hard disk vendor will release a Linux-based hard drive, and we are already working on this technology. So we are thinking about adopting this technology later this year, directly when it will be available to the public. So the other things that we can do is flexibility, okay? Because the lightweight design and the technology that we use, so the fact that we can compute this quality score, okay, we are very, very flexible. Flexible, it means that we can run on a hybrid configuration as multi-cloud infrastructures, heterogeneous clusters. So the idea that the quality score that we compute allows us to run on clusters that are made of different nodes. We can run both on ARM and x86. We can mix them in the same cluster. But actually, it's even more important the fact that we can mix nodes of different sizes with different disks without any performance impact. So this enables, of course, freedom of choice. And what is going to happen in June and July? So we are releasing a new version of our Fuse connector. This one has local caching for reading and better multi-threading, so it will improve performance. Our Fuse connector that we call OIOFS is actually a mechanism to allow our customer to import files directly into the object store and maintain one-to-one parity. So if you have a legacy application and you want to use object storage, or you plan to use objects in the future, but you are still on a file-based interface, you can do that with this component. We improved our S3 compatibility, and we are contributing back to Swift 3 project, because we think that S3 is a commodity, so the best way to show it is to give our source back to the community. We are also building a service ID directory, which is the foundation for the multi-cloud that I will talk later. The service ID directory is a major architecture change for us. So up to now, we had all the services on fixed TCP ports, and the IP of the node can't change, okay, when you configure it. After the introduction of this mechanism, we will be able to change on the fly the IP ports and the IP address of the node in the cluster, which means that we will be able to move nodes from on-premises to the cloud, or to move or to use Docker in production. And other improvements that we are doing now are container sharding, so to improve parallelism in the cluster, as well as scalability of the single container. We are working on improved storage pools. So depending on the size of the objects, you will be able to choose the right protection scheme. So this new enhanced storage pool will allow you to save very small objects in multiple replicas, and taking advantage of erasure coding for larger ones, and without doing anything, just picking up the right size that you want. And we are supporting all-flash configurations. We have customers with all-flash configuration right now, so we made a lot of enhancement and made a lot of services asynchronous to manage all the queues in the cluster internally. So more performance in general, and a new web UI that will be released later this month. I see a question. What release of Fuse? I have to check with my developer. I will send you a message later. So what does it mean multi-cloud for us? Okay, today you can install OpenIO SDS cluster, so SDS plus Grid for Apps on premises. We can do cloud tiering on Backblaze B2, but later this year we are going to support Amazon AWS S3 as a tiering level. We will be able to expand the cluster both from storage and compute, the same cluster, to the cloud. So not just tiering, but actually a full replica of the cluster. We will be able also to support only metadata instances on the cluster, which means that you won't buy EBS storage, but you will take advantage of the S3 storage, and only metadata services will be managed on EC2 cluster. In a few, oops, sorry. So this will allow us to support cloud disaster recovery. So if you don't have a second data center, you can leverage the cloud for doing disaster recovery. You will be able to have a multi-cloud strategy, because Amazon will be the first one, but actually we are going to support later Google and Microsoft. So you will be able to move to do replicas on different clouds. It will be transparent to the apps, so the same application will be able to access an application and the same data both on the cloud or on the on-premises. We will release AMIs on AWS Marketplace. It will be just easier to deploy a first cluster for testing, for example, but actually also the expansion of an existing cluster will be made on the cluster very, very easily. And we will also have this Docker supported in production. Another important thing is that we will be able to expand the cluster also from the Grid for Apps point of view. So you will be able to have Grid for Apps instances. It's a corner case, of course, but actually you will be able to expand the cluster also on the Grid for Apps applications. So I mentioned Grid for Apps many times, and I think it's time to let you know what it is and how it works. We talk very often about integrated data processing in the cluster, and if you see how the compute is evolved in the last few years, you can see that most of the virtualization platform, okay, now sometimes considered legacy. Okay, so just recreating what was possible on a physical environment, but in a virtual environment, it's getting too complicated. Okay, for some application, especially when you have this application instances sprawling, no longer in units, but actually in hundreds or thousands of small instances doing the same job. Okay, it's becoming very, very complicated to manage with the standard virtualized environment. So we had this concept of Docker coming. Okay, it's nothing new actually, but it simplifies the way. So it's very, very easy to embed application in this container and deploy this container for large environments where the compute is very, very important, and also the state of the machine is not. The problem with containers is usually that storage is still a problem. So persistent storage is still a problem in this kind of platform. And further evolution came with AWS Lambda. So you have this system that can generate an event. Okay, everything that happens at the storage level, for example, can trigger an application. This is actually what we do. So we just intercept all the event, and we trigger application in function of this event. If you look at the market, okay, and you think about general purpose hyperconvergence, okay, they are very good for a lot of workloads, but actually when the number of resources is very, very balanced, okay? But if you are looking to very specific workload, for example, big data, you are looking for a specialized kind of infrastructure. It could be converged or hyper-converged, but actually it's the nodes are totally different from what you usually see in the enterprise space for virtualizing VMware or Hyper-V kind of environment. And all flash storage is still present if you want very low latency and a lot of consistency in performance. And if you go further, you can see that in-memory storage is happening actually. So if you want the best of latency and the best of performance consistency, you look at in-memory storage, where the cost maybe is not the best, but actually it proves that you have the results faster. And on the other side, you have this kind of storage, which is improves the TCO because it can run codes directly in it, offloading some tasks from the rest of the compute environment. So we are sitting here at the moment, okay, and we are going toward this direction. If you look at the market and the object storage vendors, you will find that all the object storage vendors today can do traditional object storage, and also they can do S3, scale out, and so on. This is very easy for everyone today. And most of them are also going through an evolution of their product, and they are looking at search and indexing and big data workloads. Some of them are just exposing HDFS interfaces, or they are supporting some indexing function, okay, for the big data workloads, but actually not more than that. Because we have this event-driven framework, we can run a lot of new kind of applications, okay? Think about data normalization when you import new information, validation when you have this Internet of Things devices sending you data, or offloading some big data workloads to the storage directly, and video transcoding, face recognition, and so on. You can do everything directly on the storage. So if you look at the traditional computing, there are several layers now. Application, orchestration layer, operating system, hypervisor, or containers to manage, and the data storage down below here. And with our approach, okay, you have an application that works directly on the storage system. Of course, this kind of application is not SAP, okay? So it's a specific application written to run directly on the storage and to do specific tasks. But actually, it's really, really powerful and easy to manage. So you can find it named as serverless computing, but I like ultra convergence, even though I shouldn't do too much marketing here. But the idea is that you have just data and application that work together. So just to give you an example on how it works, think about our cluster. A file is stored in the cluster, an event is sent to the queue manager, and some processing happens automatically. So you have some content derived from this original file, and plus potentially other action that could happen. And you can save back the new content to the object store. So in the real case scenario, so a couple of weeks ago, 3 weeks ago, we had this webinar where we showed this this application. So by using public libraries like TensorFlow, we can do this. Okay, you can save an image in the cluster. It is intercepted from the queue manager. It's processed by TensorFlow. TensorFlow is a machine learning library open sourced by Google a while ago. And we add a category tag to this object with the description of the content. And also we add this on to an Elastic database. At the end, you have metadata enrichment that is saved back to the file, and it becomes searchable. Okay. Of course, if you do it for one image, it's just an example, but think about importing billions of files or millions of files in a database and have all of them categorized and indexed for searching. Okay, we have the similar use case for with a customer about indexing all the emails that are stored in our system. So this is what is going to happen in between now and the end of the year about our cluster and Grid for Apps. So each single node will have an agent. The agent will talk with a manager, and this manager will be able to do job dispatching and job scheduling, because on top of event-driven workloads, we will be able to do batch workloads. So, for example, you can launch an application every midnight to check if the files contain a virus, for example, or look at if someone saved credit cards and you don't want to have credit cards in clear in your files. And there is also a resource manager that picks up the best resource to run your application. For example, if you have only a part of the cluster equipped with GPUs, you want to run your transcoding jobs just on those nodes with a GPU. Okay, or if you have FPGAs, it's the same, or if you have machines that are used for other jobs, you don't want to use them to run your specific task. Everything will be driven by a web user interface, and we are going to add functions directly in the system later next year. So it means that we will have a specific container that will have an engine to run script that you will be able to copy and paste directly in the system. All the system will be based on containers. So all the job dispatching and job scheduling will be run on containers. So the developer just need to develop a container, and we will provide the API to let them work with the SDS, and so getting the information from the event, the object, and have the ability to change it. So with this kind of technology that we have and the product that I showed you, we are able to do actually multiple things. One is traditional installation, so data center installation. We can do geo-replication, asynchronous replications, erasure coding, and so on. So traditional object storage application. But actually, if you think about the fact that we can run on very small devices, and we have the same identical functionality, including Grid for Apps if there is enough CPU power, you can collect data and save data in a very high availability and highly resilient environment, and compute them directly when they come in. Okay, the same goes for any other sort of infrastructure that doesn't have a sysadmin or doesn't have a IT skill that can manage that kind of micro data center. Okay, think about Tesla. If you buy Tesla, they don't give you a sysadmin. Okay, but actually inside of that kind of car, there are a lot of CPUs, a lot of compute, a lot of programs, and a lot of data to store for a few moments, sometimes for a day, in other occasion for decades. So one more thing about the product is that we are an open source company, and the products in yellow are open source, and they can be downloaded and they can be installed from packages that we make available. Our product is stored on GitHub, so you can find everything there. On top of it, the file gateway, mail connectors, Grid for Apps Pro, and the web user interface, and some deployment tools to facilitate the deployment of the cluster are part of a subscription model that you can have. So let me give you a couple of examples of our installations. So this customer is an email storage system. We are talking about 65 million mailboxes. The customer has 650 nodes now. It's around 15 petabyte, and the number of objects is quite large, of course. And in the media entertainment, we just won at the beginning of the year a very large customer, and it's a 20 petabyte customer growing 30% year, something like YouTube, but it's European. And this customer is based in Japan. They are importing something like 6,000 emails per second on the system. It's a small cluster. It's 10 nodes plus 10 nodes in a remote site for disaster recovery. And I think it's a quite impressive number, 6,000 emails per second during the peak, the rush hours. And we do for each single email indexing, so the customer can search everything for legal reasons in this system. And of course, we have also very small customers. In this case, it's 60 terabyte of small files in a 3-node cluster, and it's quite interesting to see that we can maintain a very good price point also with this kind of installations. I have to say that some of our customers, contrary to what happens usually with the competition, I saw them starting with decommissioned hardware from other projects. So they just pay the software from us, because the fact that we can use heterogeneous nodes and with different resources in them make them start very, very easily. And I think that this is my last slide. So just to recap what you see. So we are really, really efficient thanks to our lightweight design. I want to remember you that we can run on one CPU core and 500 megabytes of RAM. This allows us to use the rest of the resources in the servers to run Grid for Apps. Okay, Grid for Apps is this event-driven data processing framework. So the rest of the efficiency comes from the fact that we can do multiple data protection schemes on the data saved on the system. We can have a different protection scheme for container, which is the bucket if you are coming from the S3 world, a user, or even domain space. Flexibility. We do dynamic load balancing all the time on our system. Okay, we are not locked with a fixed layout, like for example a ring, which is pretty common in the object storage design. We can run on heterogeneous cluster or heterogeneous hardware even in the same cluster. We can support ARM and x86 as well if you are running Grid for Apps, also GPUs and FPGAs. And we have automated tiering, both internally in the cluster as well as to the cloud. And with the next generation of the product, we will support public cloud and multi-cloud. Hybrid tiering is already available in the system today, and as well as multi-geo. And low TCO because open source, software defined, so you can have different you can split the hardware from the software, and the system is really easy to use. 3-node cluster can go up in 5 minutes, and adding and removing nodes is a very simple task. I did it, so I know that if I can do it, anybody can. And that's it. Okay, if you have any question, I'm here available, and my colleague Guillaume joined me. He's the head of pre-sales. So.
Hey everybody. So we already have a couple of questions. The first one from is if you use indirection, does that mean that you have to do an equivalent to FSCK if you get data corruption? So when you, for example, when you lose a disk on your platform, we have all the tools to rebuild the data. So from my perspective, it's not like an FSCK, but it's yes, it's almost the same. Is if you lose, if you are in a if you use an erasure coding configuration, yes, we will will rebuild and reconstruct the data from the parity chunks. I think it was talking about if it's about metadata, no, it's data corruption. So, and for the metadata, it's almost the same. We have a table of indirection that is also distributed and replicated. So if we lose a disk with metadata on it, we will be able, using almost the same tools, to take the metadata, the missing metadata from another location, and to write it again to make sure that we will be compliant with the security configuration that you put. By default, we are replicating 3 times the metadata. So what release of Fuse are you using? So yes, it's a 2.9. The web user interface for demo, free environments limited by number node and capacity. So no, the web user interface is not open source. It's not free, if you can say that. This is something that we are providing to our customer when they are taking the subscription at OpenIO. It's not something that we are directly selling. It's really something that we are giving with the subscription. The only thing I think that what Enrico wanted to say is that for our partners, we can provide you a demo version for our partners to test it, and for you also to be able to showcase it in front of your own customer. If the answers are unclear, or if you want more details about the answer I'm giving, feel free to send further question about it. New question, you talked about Swift compatibility. So my mind goes to OpenStack. Can you make a quick comparison, pros and cons, with the OpenStack storage system, and will it be OpenIO compatible? So one thing very important here is that we didn't redevelop Swift Gateway. We put our APIs, Python APIs, directly into the Swift Gateway. So yes, of course we are compatible because of it. It's not we don't redevelop something from scratch. So we are fully compatible with the Swift Gateway, the open source one that you can find on GitHub. And the main difference we have with Swift, I guess the storage system of OpenStack is the Swift one. The main difference is that Swift is based on a static algorithm to place the data, and OpenIO is based on what we call a smart load balancing, dynamic load balancing, meaning that for every node and at the end every disk of the platform, we are computing a quality score between 0, which is the worst score, and 100, which is the best score. So every time you have to do and to perform an operation on your cluster, I mean to read or to put a data based on this score, we will choose, every time you have to perform this operation, we will ensure that this operation will be made on the best disk and most available disk of the platform. So this is something really a strong differentiator, because we don't have a key space where you put, for example, if you have 10 nodes, each node will take 10% of the load and take 10% of the data. With OpenIO, with this scoring system, for example, if you have an heterogeneous platform with one node which is twice better than another one, we will put dynamically, I mean, you don't have to configure anything, dynamically put twice much load on it than let's say the old hardware. And the last thing about it, and it's really key, is when you have a key space with 10 nodes and each node will take 10% of the data. When you scale it, you have to reshuffle your key space. I mean, you have to, if you scale to 20 nodes, each node will take at the end of the day 5% of the data, and you have to recompute your key space, and then you have to reshuffle and move your data. So you will have to, what they call the rebalancing operation. With OpenIO, adding a new node has no impact. Doing this rebalancing can be really painful because your disk will be busy at rebalancing the data, not at serving the data to your application. And so it could be painful if you do it quickly. Your disk will be really busy, or if you do it slowly, it will take a long time to do it. OpenIO, when you add a new node, it has no impact. The only impact it has is the new node will have a better score because it's a new node without any I/O on it, any capacity. So this new node or this new disk will have a really good score, and we put more load on it, a bit more load on it, and the platform will tend to become homogeneous by itself without launching any rebalancing. So the good point here also is that as it's really easy and that it has no impact to scale with OpenIO, you can really do it often and really when you need, because it's not painful, you don't have any impact, so you can really do it when you need it and when it's important to do it. So you can really also scale as you grow. And we have some of our customers that are scaling at the disk level. So yes, it's really something that you can enable.
Okay, I just want to add that most of our customers are scaling their clusters with so the new node usually are different from the older ones. So they don't have any sort of problem by mixing different disk size, different CPUs, and different, even sometimes different Ethernet types. So that's it. Any other question?
Yeah, one thing to add to what said Enrico is that yes, because when you are building an object storage or distributed storage platform, you are building it for 5 years, 10 years, maybe 15, but you are not building it for 1 year. So you are at the very beginning of your platform, you already know that the hardware you will put in your platform in 5 years will not be at all the same that you have today. So your platform will for sure become heterogeneous sooner or later. So it's really important to have this ability to drive the load, taking care of the capacity and the performance of each hardware, because your platform will become heterogeneous for sure.
Okay. Thank you very much again for spending this hour with us. I will send you a follow-up email with the recording of this session, as well as links to our YouTube webinar with the TensorFlow demo, so you can see in practice how it works, and a copy of this presentation. Thank you very much again to everyone.